Problem 10. The figure below represents a graph of the electric potential in volts in a region of space versus position x. Position x. God, it sounds so mysterious. Where the electric field is parallel to the x-axis, which is shown in centimeters. Okay, what is the electric field at 0? Where is the electric field? 0. Might actually be 0 at 0. Anyway, all right. So here, I'm going to write up our formula. So we have voltage equals negative integral E dot dr, which in turn means that electric field equals negative divergence of voltage, which is basically the derivative of voltage. You do the integral here. To get rid of the integral, you take the derivative. So these are supposed to be vectors. I'm too lazy though. I'm not going to put them on. So the idea here is the derivative of voltage is the electric field. Voltage is the negative integral of electric field. Voltage is the negative integral of electric field with respect to R. Okay. So we need to, so it asks us where is the electric field 0? So where does the derivative of voltage equals 0? Actually, since this is just a graph, I'm going to do negative dV dx. Bam. There we go. Since we're just doing it in the x direction, I don't have to pretend like it's more universal than it is. It's just dx. So where is the derivative voltage with respect to x equals 0? All right, so you get the derivatives equal 0 at, so where's the slope equals 0? When the derivative equals 0, slope equals 0. So we're going to look at between 3 and 5 and negative 2 and 0. So at x equals plus 2? No, false. At both? I probably mean at both 2 and 4. No, because it's not 1, so it can't be that one. And x equals plus 4. Yes, at x equals plus 4. So this guy right there, check. Or x. What is the electric field at x equals plus 6? Positive values represent electric fields in the x direction. Okay, so here we're going to have to find the derivative with respect to x at plus 6. Okay, so we can do that. So going back to, so this guy right here is 2, and I think it's 2 volts. All right. Below represents a graph of electric potential in volts. So this is 2 volts. And then this is, let's see, 1, 2, 3. 8 minus 5 is 3. So I'm going to say 0.03, going smaller, meters. Because it's measured in centimeters, and we need to convert it to meters to get something like meters right there, like they said. Something more standard. All right? So volts per meter. What is the electric field? Okay, we got this. Bam. So now we just got to do rise over run. So I'll do 2 divided by 0.03. 2 divided by 0.03. 66. I'm going to call 67. All right. So don't actually put in 67. Put in a bunch of 6s just to make the computer feel good. All right. So that was how we did it using just straight math. Using it logically, volts divided by meters, be like, well, the volt change is 2, the meters change is 0.03, so we're just going to do 2 divided by 0.03. That's dimensional analysis, which it's useful for graphs. If you have a graph, do dimensional analysis, and that way you can either check your answer, or if you have no idea, it gives you a better shot in the dark. All right, what is electric field at x equals -1? So -1, bam, 0. Rise over run is 0. Actually, I think that's supposed to be negative. So going back to the maths, electric field equals negative derivative. So it's going to be negative rise over run. So negative 67 volts per meter. All right. Now consider the electric Now consider the figure to represent the electric field in newtons per coulombs instead of potential. What is the potential difference between +2 and -2? What is the difference in potential between +2 centimeters and -2 centimeters? Okay, so now go back to this graph. Bam, erased it. So now that now we can start clean because now we have, this represents electric field. Whoop. Big E, newtons per coulomb. Okay, so I'm going to write up our formula. Actually, I'm going to start by writing the formula down here. So the definition of voltage is bringing a test charge from infinity to a point. So this is going to be infinity to 2 through an electric field. And then we're going to compare that to another location where we also brought a point from test charge from infinity to -2. All right? And then E dot dr. So in the grand scheme of things, I just canceled the double zeros. In the grand scheme of things, getting the number for this is going to be really easy. Like, oh, it's an integral. It's area under the curve. Not a problem. Yep, count the little boxes, add up the little boxes, and bam, you got it. The problem is this going to be negative or positive? And the thing here is electric fields really aren't negative or positive, so to speak. What they are is left or right. So I'm going to draw my favorite electric field here. Nope, I'm going to use a square. And for those of you who don't know yet, my favorite electric field is one that's created by a capacitor or parallel plate. Okay, now I'll do black. I like black. All right, so now we got our parallel plate capacitor, copy paste, move this guy over here, put in some charges, another charge, another charge, another charge. Bam. There we go. Put some opposite charges on this guy. And what we get then is an electric field that goes from the positive. I probably should make this guy formalize it a little bit more. Ooh, I like that arrow. Right there. Bam. This is the direction of the electric field. This way. So electric field goes from left to right. So what this is asking in, I'm going to say right here is infinity. I know it's not infinity, but might as well be for this. It's asking, so if this is our point that we're going to, I'm going to call this point A, and this is point infinity. Oh, should probably just make an 8 and turn it sideways. It's what's the energy required, the joules per coulomb, to bring it a test charge, positive test charge, from infinity to this point. And so what really matters, so it's going to, obviously if we have a positive test charge and we're moving it towards the positive plate, that's going to take a lot of energy because same charges repel. So this is going to be a high amount of energy, a very positive energy. So then we look at our formula. Yep, right here. Here's the same idea. So what really matters here for E dot dr, what this is really asking is E and R in the same direction or not? It's not asking is E positive and R, the direction, positive. It's asking is if are they in the same direction. So for example, so we know E is going this direction, and then our test charge is moving the opposite direction. So it's going to, if they're moving in the opposite direction, we should get a high voltage, high joules per coulomb. So what happens is the E dot dr gives us a negative value. And that negative value times this negative then gives us a high voltage. And that's how you get a high joules per coulomb. So that's the way this formula works. So what we have here then is we're doing an integral from 0 to 2, and I'm doing from infinity to negative 2. So I'm going to start from infinity to 2, and I'm going to look at what this guy does. So starting at 2, I'm going to draw a line straight up and down, so we got kind of a point to work with here, line of reference. Yep, except my line is all crooked. And make it a little bit straighter. There we go. Call that good enough. I probably could have done that much better. Okay, I'll do it well. There we go. Oh. There we go. Then I can just copy and paste and use that guy again later. Now it even looks more crooked than before. Not important. All right. So if we go from infinity to 2, I'm going to say this takes us 1,000 joules. So to take a particle, go to here. I'm going to say it takes us 1,000 joules. In the grand scheme of things, it won't matter, or joules per coulomb, because we're looking for the difference between 2 points. All right, so then the other point they asked us was negative 2. Negative 2? Negative 2. So we're going to go from infinity, which is out here. By definition, infinity is greater than 8, over here. And we're going to go take a particle, go all the way over here. And this is, we know this portion right here is going to be 1,000, but we need to find this portion right here. So we have 2 times 4 divided by 2. 2 times 4 is 8, divided by 2 is 4. And we have 2 and 4, that's going to be 8. So we're going to have a total of 12. 12 additional joules per coulomb here. And so this is positive, which means, and this is from right to left, the positive electric field here means that the electric field is going from left to right. So I can even draw down here the electric field. I'll do some green just to, electric fields feel like they should be green. So the electric fields over here will be going this direction. The electric fields on this side will go in this direction because the electric field is negative. And that's what it means by the positive or negative electric field. So in this case, the test charge and the electric field are in opposite directions. Therefore, it's going to be negative. So this portion right here is going to be negative. Negative times negative will be positive. So the 12 that we had right here is going to be positive. So if that took us 1,000 joules per coulombs, this will then take us 1,012 joules per coulomb. All right? So right here, we said this guy is going to be 1,000. So to take a test particle from infinity to 2 is going to take us 1,000. And then to take us a test particle from infinity to negative 2 will take us 1,012. And we decided it was positive because the field, electric field, and the motion of the test particle are in opposite directions. Therefore, it's a positive times a negative because it's a negative. But then our formula also has a negative, which gives us a positive. So the idea here then is we got 1,012 minus 1,000, which equals 12. So we'll have 12 volts. So again, the number portion of this problem, really easy. Just count the boxes under the graph. The hard part is determining the sign. Okay, so now they're asking, what is the potential difference between 8 and 0? Okay, so we're going to have the same equation we had right up here. Oh, copy those guys. Copy, paste. Yes. Even got most of it. And we're going to do 8 minus 0. So this will be 8. Doesn't look like a very good 8, but that's okay. Get the idea. And 0. So we're going to do the same concept up here, though, as we did up here. So copy, paste. Take this guy to 8. And then 0's already kind of got a line by it, so I'm good with that. All right. So I'm going to say to get to 8 will take us, I don't know, maybe we could probably actually figure it out. I'm going to say 0. I'm just going to go Yeah, whatever. So this, to take a particle from infinity to 8, I'm going to say takes us, I'm going to switch over to red. Magenta. All right. So probably don't need this arrow anymore. To get from infinity to 8, I'm going to say it takes us 0 joules per coulomb. Okay? Because we don't know what's out past there, we'll just say it flatlines. And now we're going to have to find out how much it takes to get to 0. All right? So we already know this section right here, that's 4. But now we need to break this portion up and make this. So this is 1, this is 2. 1 times 2 is 2. 2 divided by 2 is 1. So that triangle is 1. All right? This guy here, that 8 is really convenient. Okay. Yep, 8. So this, it's 2, 5 and 3, times 2, which is 4. 2 times 2 is 4. All right, 1, 2, 3. 3 times 2 is 6. 6 divided by 2 is 3. 1, 2, 3, 1, 2. Make sure that actually leads to 2. Yep, 6. Okay, so we have 6 here, and then here we already counted out. 2 times 4 is 8. 8 divided by 2 is 4. Because the formula for an area of a triangle is 1/2 base times height. Okay, now we add those together, and we get the 4's cancel out, and we have 1 and 3, which is 4. Okay, so we know that we have 4 more on the bottom side than we do on the top side. So whatever voltage is contributed by the bottom side will be the part that dominates. All right, so if we take a test particle and move it from infinity this way, it's going to be with the electric field. And being with the electric field, that means E dot dr is going to be positive. So if a positive times a negative will then be negative, so voltage will be -4. So the end result of all this will be, go down here, get some magenta, it will be -4 volts. -4 volts. All right, so now that you have the understanding of this, you probably should just use a rule of thumb. So look at this problem and say that, all right, this top portion is going to be positive voltage, this bottom portion is going to be negative voltage. And that way, whenever you see this on a test, you don't have to go through all this logic. And like, all right, so these will be all positive, these will be all negative. And it's easy to remember because positives on top, negatives on bottom, that seems reasonable. And I would go into the test kind of with that mentality of, this is the thumb rule, conceptual understanding, don't care, and just take what you need to win on the test. So let me go back to this guy real quick. So this guy is 0. This guy we know is, we decided B was -4. And we have -4 plus 0 is -4. So, and that the thumb rule I apply, that, you know, negatives, the bottom. If it's below, if you have a negative electric field, that you get negative voltage, and if it's above the 0, then you get positive voltage. That only applies if you're doing a bigger number minus a smaller number. So you have to be kind of careful when you're going through it. But if you have a problem set up exactly like this on a test, then try and use this thumb rule. All right? So if nothing else, you can always get the numbers right by just understanding that you have integral for the bottom using this formula. All right? Hopefully that wasn't too confusing. I understand with the signs for this kind of problem can get kind of confusing, and you're trying to mix formulas with actual concepts, and sometimes that can be disastrous. All right? But I would recommend looking at this problem, understanding it as best you can, and that way when you come across it in a test, you can at least fumble your way through it. One quick catch before we move on. The when we were just finding the area under the curve, what we were actually finding was electric field times distance, and the distance is in centimeters. So when we convert this, we have to convert the centimeters to meters. What we're going to do is divide by 100. So it's actually going to be 0.12 volts and 0.04 negative 0.04 volts. All right, now that should do it. And on to, was it problem 11? Problem 11's next? I think, yes. On to problem 11.